I stated a theorem about the bound, the lower bound, about the dimension of a rather generic component in the character variety of three manifolds with boundary. There was one last step to do, so I will recall the statement and recall where we were 2 days ago, and then I will use this statement as like an incentive to broaden up the perspective and analyze more this character variety, at least for hyperbolic manifolds, cusped hyperbolic manifolds. So, recall from the last time that we were looking at a three manifold, compact, with boundary, I should say non-empty boundary, and in the boundary we assume there were T tori, and we have the fundamental group. So we looked at the character variety of gamma, this time not as in Johan talks, but in higher rank groups, and in fact you can put, more or less you can put any reductive, linear algebraic reductive group here. And the theorem was that if x0 is a component, an irreducible component of this one, containing a strongly irreducible, so recall that the morning Johan defined irreducible, and for strongly irreducible you ask for every finite index subgroup of gamma to have irreducible image. Strongly irreducible and boundary regular, I will recall it later, representation. So you are looking at a single component of the character variety, but not anyone. You have to know that inside this component there is at least a non-degenerated representation. For example, non-finite representation. A finite representation will not be strongly irreducible. And you don't want the representation, when restricted to the tori, to be too small. Okay. But if you have this representation, you can speak about the whole component. And you can have the lower bound, which is the same that appears at the end of Johan talk, which is the number T of tori times the rank of the group, here is n minus 1, minus the Euler characteristic of M times the dimension of the group. Okay. So this was the theorem. Which is due for n equals 2. I don't want to use this one. For n equals 2, this is due to Thurston and Culler-Shalen, and then we managed to generalize it with Elisha Falbel. And let me just recall the very nice geometrical idea to the idea of proving this theorem by induction on the number of tori. And in order to destroy one torus in the boundary, we analyze the fact that we should choose well some gamma inside big gamma, and drill along gamma inside n. And when you drill along gamma, you construct a new manifold, and this torus boundary becomes a genus 2 boundary component. So you have one torus less in the boundary, and so we analyze that we can use the case t minus 1 for this new manifold, and we've seen that if we can choose gamma such that when you look at the subgroup of big gamma generated by the fundamental group of this torus and the loop you've chosen, this should be irreducible. If we can do that, then this theory is proved. Okay. And I just recall, without writing anything, that the key point was to restrict everything to the genus 2, restrict every representation to the genus 2 surface, and then arrive in the realm of surface group representation, which is a very well-known topic. And we were in this restriction, so in this setting we were able to compute codimension, and we were able to pull back the codimension that we computed inside the surface to a codimension for the three manifolds. So it was just a reminder, but now I would like to explain how it is that you can choose such a gamma. Recall that P1 of t generically is the diagonal. Okay, I made the assumption, so, and generally I made the assumption that it was regular. It is where the boundary regular assumption shows up, which means that, so you can, let's just think at the diagonal case, diagonal with distinct eigenvalues. The key point here is that it implies that this subgroup of SLN has only a finite number of preserved subspaces, stabilized subspaces in C to the n. Okay. In the diagonal case, you have the eigenlines and then the sums of them, but it's still a finite number of eigenspaces. And in the other case, other extremal case, which is unipotent with a unique Jordan block, you have only one subspace for each dimension. The eigenline, and then the only plane, and so on. Okay, so this is a key point. And if you want to work with a general linear algebraic group, you have to look a bit at Steinberg works on regular elements in linear algebraic, reducible algebraic groups. Okay. So, but anyway, here we have this. We know that this guy has only a finite number of stabilized subspace. So what are we looking for? We are looking for a single gamma which is not stabilizing anyone. But this is not that hard. You have the whole image rho zero of gamma is a big group in SLN. It is at least supposed to be strongly irreducible. And for this proof, I will further assume, for simplicity, I will assume a very strong form of being big in SLNC that I will assume that it is Zariski dense. But in examples, you often have Zariski dense representations. So this is just a simplification assumption, but sometimes it can be already useful to have this. Okay, so now I know that rho zero of gamma is Zariski dense, and so for any of these subspace, let me write that. For each invariant subspace by the torus, rho zero of pi 1 of t. The set of matrices stabilizing it, this set is a Zariski closed subset. I don't want to pick gamma inside this set, but and inside any of this set. So consider I take the union of every element in the SLNC that preserves at least one invariant subspace. It's finite. So it's still Zariski closed. And it is not the whole SLNC. It's not open. So there exists someone in my Zariski dense set which is not in the Zariski closed. Okay, I have just a finite number of Zariski closed condition from one part, and from the other part I have a Zariski dense set. I can find someone, and in fact a lot of guys that does not behave bad. Okay? So here we are. We take such a gamma, and we drill along it, and we make our computation of yesterday, and we have done the induction step. Okay, so it's a kind of cheating because of this Zariski dense assumption, but In the case you just want strongly irreducible, well, you have to play with Borel subgroups and intersection. Well, it's a bit more technically involved, but there is no problem. Well, there is no problem, but there is for these steps that you need strongly irreducible. If you have just an irreducible representation, this step could fail. And indeed, Stefan told me a nice example for white ethnic complement inside PSL2C and not SL2C, for which there are some single irreducible finite representation which are boundary regular, but which are single points of the character variety. So, thanks to Stefan, if you drop the strongly irreducible assumption, well, it works for SL2C, but it doesn't work for PSL2C. So it's really needed, even for hyperbolic geometry. Okay? Okay, so, well, we see this proof, but now let's try to have a kind of a bigger picture. In my opinion, a key technical point in this proof is to be able to push everything on a surface group. In some sense, it's very hard to work with character variety of 3 manifold groups. But as soon as you can say something about surface group related to some surface group problem, well, you have done a good work, and then you can try to work with all the theories that can help you in a surface group representation theory. So I will define some things. Are there any questions on this part? Well, it was a bit like, it was a beginning like tough, you know. We were, from the beginning we were looking at a very precise statement, but let's step back a bit and talk about peripheral holonomy. So here I will restrict myself to a narrower setting. I will assume that M is cusp hyperbolic manifold, 3 manifold, orientable, and so I state it like that, but I strongly have in mind knot or link complement. From now on, for all the lecture today, M will be this one, gamma will be its fundamental group, and I will denote the boundary of M. Well, I should have said that M is the interior of a compact with boundary manifold, whose boundary is that I will be a bit sloppy. Okay, we have cusps and we have torus for each cusp that I denote Ti, and I don't know why I did that, but okay, it was necessary. Okay, and now when you have a representation, let's stick to SLNC, or sometimes I will write PSLNC, but okay. When you have a representation, you can look at its restrictions. I want to the different fundamental group of tori. So you have a representation and you have a collection of Z2 inside the fundamental group, inside gamma, the fundamental group of the manifold, and you can restrict representation to this Z2. Once again, you have to choose. There is no canonical injection from this one to P1 of gamma, so you have to choose a representative. But this is not a problem. This is not a problem. And you have, so doing that, you define a map, which I call peripheral holonomy. It's quite clear why I want to call this peripheral holonomy. And so this map takes the conjugacy class, almost the conjugacy class of a representation of gamma, and lands inside the character variety of these guys. Of the same group. Okay. So from this side we have, well, the object of interest for this talk, the character variety of gamma, and here, if G is SLN, it's merely some, it's almost C to the 2n minus 2 k times. Each one of these guys is C to the C star to the 2n minus 2. So this is almost C star to the 2n minus 2 to the number of 3. So this is not so complicated on this side. And the general question is general and very vague question is how much information you can read for a representation just through the peripheral holonomy. If you are not used to this kind of problem, it seems completely hopeless to have a good answer to this question. You have the representation of a whole, let's say, not complement, and you are saying, I'm just looking at what happens for the Z2 over there, and I would have to know something about the whole representation. It seems hopeless. It's the image seems to carry very little information. However, you can say a lot. So let me give some examples of what you can know through this peripheral holonomy map. And for that I will recall the geometric representation and what I will call the geometric component of the character variety, which is more or less what Johan called the distinguished component this morning. So recall this one. you have, in this setting, you have a preferred representation, which is to go first inside. Here, I guess I will be safer to look inside projective, especially in our groups. So this is the hyperbolic holonomy. Okay, the holonomy of the unique, complete hyperbolic structure on M. So this is a representation. And now you can jump to higher one group, just using the unique. Well, unique always means up to conjugation. The unique, irreducible representation. So maybe you are not so used to this representation. I will just give the example in the case n equals 3. So for n equals R3 is also called R. It's the adjoint representation. So SL2, PSL2, acting by conjugation on its Lie algebra. Okay, the image being what should I say? Okay, SO2. Okay. Okay, and then you have an equivalent of R3 of the adjoint representation for each dimension, for each n. You can look at the action of SL2 on the homogeneous polynomials in two variables, and it gives you an irreducible action of SL2 on the space Cn, and so it gives you a map, an irreducible map from PSL to C inside this one. Okay. And it happens that this map is unique. Okay. And if so now I can just, maybe I should another one. Go all the way, and this I call the geometric representation. Okay. So there are choices of conjugation, but at least in the character variety, its class in the character variety is well defined. Okay. It was a point that Johan showed us this morning for the 8-knot complement case inside PSL2C. And we can look at its component. So here I'm a bit sloppy. You can prove that there is only one component of the character variety passing through this point, and so it defines some component of the character variety for any SLN, and I called it the geometric component. Maybe I should call it more the distinguished component. But anyway, this component. Okay? Is there a question?
I guess you should say that M is oriented rather than orientable, but in order to really get the unique.
Yes, you are right. Okay? So I will focus mostly on this component of the character variety. As Johan told us this morning, this one is well behaved. If you are wanting to look to the whole character variety, you are going to see more and more strange stuff. So it's very hard to speak to say something useful, very general on the character variety. So I will try to focus on this component and say what can be said of this component through this peripheral holonomy map. Okay? So here's the first theorem. Let me state the theorem and then we will speak of who did that. So here you are looking at the image of this component inside by the peripheral holonomy map. And okay. And you are looking at this map only around the geometric representation. Is a bijection on its image. Okay. So this is a lot. This means that if you want to deform the geometric representation, you just have to decide how you deform the representation inside the cusps. Okay. And moreover, you cannot do anything you know something about its image. Its image is a Lagrangian submanifold, well, an open patch inside the product. So here I am, maybe I'm going too fast. This is I should say isotropic. I will say that just what should I say? Sorry. Sorry. Let's see. A cadet dimensional isotropic. It's a manifold. Okay. What I am. Okay. So sorry. I have to think a minute. What should I say? So. Let me write something and then I will speak. I will be able to speak. Okay. So what I am trying to say is that when you are looking at the image here, it has half the dimension, and here you are in a product of character variety of surface groups, so you have a natural form. And you are, which is a product of, it's a Goldman form for each torus. And you are isotropic for this form. Okay. So well, maybe I should not have talked about this isotropic stuff. What is more interesting to me is this dimension. This dimension is exactly the lower bound given by the theorem. The theorem says some component which contains a non-two degenerated representation, and this one is non-two degenerated, it is irreducible, and boundary regular has dimension more than the number of tori times n-1 plus the Euler characteristic stuff, but Euler characteristic of M is 0. So you just have to look at what happens to the tori and you just have the good dimension. So this theorem at least states you that the bound is sharp for every SLN. I don't know if the bound given by the lower bound given is sharp for other groups, other stranger groups, but at least for all SLN it is sharp, and it is attained by this component. So here it is. I think that for SL2 it follows from work of Thurston and Neumann-Zagier, but I think it Choi who did that. And for n greater than 3, it's the work of Menal Ferrer and Joan Porty. And the theorem is more precise, is that it gives you local parameters. So it gives you exactly, you have to decide more or less, in each torus you choose a longitude, and more or less you have to decide the eigenvalues, how you deform the eigenvalues of the longitude, and it gives you the whole deformation. For every choice of a deformation of the eigenvalues of each longitude, you have only one representation of the whole manifold which is compliant. So in some sense, at least locally, you can read everything through peripheral autonomy. If you are just interested not really in the whole character variety, but just in deformation of the most natural representation, you can see everything through this peripheral autonomy map. Moreover, there is another approach. There is a more combinatorial approach to this problem that I made with Elisha Falbel and Nicolas Bergeron, and which gives you another insight. It gives you an experimental insight to this problem. So I won't describe it precisely, but using a combinatorial approach, I will speak a little bit later of this, what kind of combinatorics I am speaking about. But you can actually compute on some examples tangent spaces to some point in the character variety and check if the same theorem holds. Okay. This property, I like to call it local rigidity, meaning that locally deforming representation is rigid once you decide what you do in the tori. And the problem of local rigidity for representation of some not too complicated groups of not too complicated manifolds inside SL3C, okay, you can just compute by hand tangent spaces and the problem of the peripheral autonomy. Okay, and this has applications. I will briefly it's a forthcoming paper with Pierreville. So, in case of, maybe I should just describe it by hand. You take some kind of this manifold, so the white-head link complement, which is definitely in this setting, and for some reasons, Pierre happens to have some representation inside this character variety. That's a character variety for the white link complement inside SL3C. Indeed, its representation came from complex hyperbolic geometry, so it was into SU21, but okay, it's inside SL3C. And he saw, I will just say it, he was able to, by hand, compute a 4 parameters family of deformations. Okay, so he had a 4-dimensional family of representation inside this character variety. And being able to compute actually the dimension, the local dimension of the character variety, we can check that his family is actually a whole component of the character variety. So you can prove just by computing dimension, you can prove the following property, which is nice, I think. Well, which is not that important, but it is a nice example. So you can prove that there is a component, a whole component of this character variety where every representation, in fact, factors through a quotient, factors through the quotient of this group, and it is a very good understood quotient. What is this quotient? Well, you take your white-head link complement and you make a double denser jury of slopes. Both slopes are the same and are 3 minus 1. So let me speak around that. So you have your white-head link complement. There are 2 nodes. There are 2 tori, and for each tori you glue a solid tori deciding the slope, which is 3 minus 1 in snappy parameterizations. So doing that, you construct a compact manifold, which is not hyperbolic. And there is a whole component of the character variety for this big group that indeed is made only of representation of this smaller group. It is a quotient. Okay, so you cannot deform in order to not have this additional relation of denser jury. Okay, so I think it is a nice example. And moreover, you can do geometry in this example, and you can construct. There are examples of Schwarz and of Falbel of nice, what is called shear structure on the white-head link and on denser juries of it, which comes from this component. Okay, so the point of speaking about that is you have a general theorem, very beautiful, but you are also able to directly experiment with some representations. So experimentation is not so easy because these variety are big. The ideal defining it once you go into SL3 and even after it's bigger. So it's not easy to experiment, as Johan told. Computing into SL3 is not so easy, but it can be real. It can give real insight into the structure of the character variety, and it can be more than help. It can help geometers, and in this case, complex hyperbolic geometers, to construct new geometry in this for manifolds. Okay. So and you can find the 8-node complement inside this one. Okay. So I won't go into that, but it's almost the 8-node complement example. Okay. Okay. So I would like to state another theorem about whole peripheral holonomy map, which for now holds only for the case n equals 2. So this is theorem dense field. And Clough-Tillman, the spelling is correct for Clough? Oh, yes. Ben Clough. Okay. Which says that when you look at the map all Paris, and you will only look to the geometric component, and you are looking to this time it's not a local theorem, it's you are looking to the whole geometric component and to its image. This is a directional map, which is the best you can have for an algebraic map. And I have to say that this image, in the case of a node complement, is well-known A polynomial. Okay. The A polynomial is exactly this sub-variety of C2 more or less. Okay? And, well, you can read a lot through the peripheral holonomy map. You can read the whole geometry, algebraic geometry of at least the geometric component. And in some sense, it answers to your question this morning, that what do you know of the geometry of it? It is the same question of what do you know of R polynomials. So it gives you an idea of what is the question here. Okay, it's exactly a question about R polynomials, so there is a lot of work. And I should stress that it is only proved for n equal 2 for now. And question, maybe conjecture, I don't know. Is it still true for greater n? I have not such an imagination, so I keep trying to generalize things that are known for SL2 and analyzing if the techniques used for SL2 may generalize for general n, and it happens that in this case the techniques as the proof as they are done cannot generalize in a very nice way. So I hope I will have time to speak a bit more of this question at the end of my talk. But okay, I hope that, the philosophy of this part is that you can read a lot just restricting to surface groups, and it is something that you should try to do when you have a problem. Okay. Now I will shift to what will seem a different topic about the character variety. I will shift to volumes. And so I will review, I will give some hints for a definition of a map from the character variety to R, the real. So there is a map, continuous map. And most often real analytic, there is a map from which I call volume, from those character varieties we are talking about into R. Okay, so let's try to understand this map. There are several definitions, but for the moment let's stick to the case SL2. So let's stick to hyperbolic geometry. So there is at least one point where you know what this map is. The volume of the hyperbolic holonomy, which I still did not review. Here's the hyperbolic volume. Okay. And as Johan taught us this morning, when you are moving on the character variety, you are deforming the complete hyperbolic structure on M to a non-complete hyperbolic structure. And since M is non-compact, it is a cusp hyperbolic manifold, it is not clear why you could still have a volume if you deform the hyperbolic structure. So there are two approaches to this problem, and well, no, there are many approaches to this problem, but I will present two approaches. One combinatorial approach and one more technically involved approach, which both have a very important consequence. So maybe for me the easier is the combinatorial approach. And I have not drawn any tetrahedron yet, and I'm not used to it. Usually the first thing I do is to draw a tetrahedron, so I will draw a tetrahedron. So let's try to understand what is the volume. And let's make it on an example. And here Jeff will be happy. I will take the 8-knot complement. Okay, and I will, well, this approach is a Thurston's approach. So I will triangulate it. And here I need my notes. So it's a fact due to Riley that the 8-knot complement can be seen as the gluing of two tetrahedra where you just drill the vertices. Okay. So let me describe this gluing for sake of completeness, and I'm trying not to be wrong. So this is a topological assertion that if you look at the combinatorics of the arrows, each face has a unique combinatoric, and one face here corresponds to just one face there. So you glue together the two identified faces, and well, this is a non-trivial fact, which is very interesting, is that when you do this procedure, you get a three-dimensional manifold, which is homomorphic to the 8-knot complement. And you can do that for almost all hyperbolic manifolds. Okay. So now, how do I put some hyperbolic structure on it? And a lot of you know that by heart, but let's do this. I'm not done with this board. So, what does that mean to have a hyperbolic structure on M? Well, if I have a hyperbolic structure on M, I can just, it will give me a hyperbolic structure on an ideal, it will give me the structure of ideal hyperbolic tetrahedra for these two tetrahedra. Okay, so these two tetrahedra will become some ideal hyperbolic tetrahedra, meaning ideal means that the four vertices lie on the boundary at infinity, which is CP1. Okay? And the other way around, if these two tetrahedra are realized as some hyperbolic ideal tetrahedron, I can try to glue them inside the hyperbolic geometry. And I'm not sure if everything will be compliant. We will go into that. What should we ensure to be compliant? But at least I will have some kind of singular hyperbolic structure. So it was not very precise, but I hope that at least you have some insight on the fact that constructing a hyperbolic structure on the M is directly related to giving to each tetrahedron the shape of an ideal hyperbolic tetrahedron, and the shape of an ideal hyperbolic tetrahedron. Forget about it. And now, as I said, you cannot just take any pair of hyperbolic ideal tetrahedron, because when you start to glue them together, inside M, on the topological side, when you start going around an edge, after some steps, here is 6, I think, for both edges, you will go back to the initial tetrahedron. Okay? So you can, when you look from the topological side to when you loop around an edge, there is only a finite number of steps, and this should reflect inside the hyperbolic geometry. So for each edge, you have a condition more or less saying that when you glue 6 times this and this and this and so on, you should go back to the initial point inside H3. And this happens to, you can make computation with holonomy matrices. And this happens to give you an equation. In fact, 2 equations which are related. So in this case, you see that, am I correct? Well, for some choice of normalization, it happens that the equation, the condition you have is this one. Okay. So it gives you algebraic curve inside C, and for each point in, more or less for each point in this algebraic curve, using this method you construct a representation. So you have something of dimension 1 inside X geom, inside the geometric component of the character variety, but in this case it is of dimension 1. So this is almost the same. I'm a bit cheating, but not that much. This is almost the same than X geom. And then, okay, and then you can, I will not do that now, but you can look at the unique complete hyperbolic structure, and you can just find the solution for Z and W. Okay, so this is a combinatorial approach. You have more or less, well, it is another way than Johan told us, but it is another way to compute character varieties using what is called Thurston gluing equations. Okay, now what about volume? Well, I will cheat a bit. If I have such a point in my component, I see my manifold as the gluing of two hyperbolic tetrahedron. But an hyperbolic tetrahedron has a well-defined volume for the hyperbolic volume. And it happens when you know its cross ratio, it is given by a function called the logarithm. So you want to say that you just sum both volume. You see your representation, your hyperbolic structure behind your representation as a gluing of two tetrahedron. Well, you just sum up the volume. And this defines a map on this component of the character variety. Okay. And well, in fact, in general, you can see when you do this. First of all, you can do this in a very general setting, and it is what is behind the software called Snappy. And so in general, you see some components of the character variety. You will never see the abelian components that showed up in Johan computation, but you are seeing some components doing this trick. So here, in this case, you see just the geometric component because it's the only one to be there, apart from the abelian component. But well, in some sense, you have defined some volume on at least some component of the character variety. Slow, but anyway. And moreover, you can, in these parameters, you can rather explicitly compute this peripheral monomy map. Indeed, what you have to do is you take some point in the character variety, so some z omega, cw, and you want to decide what are the eigenvalues of the longitude and of the meridian. So it is not very well defined like that. You don't know if you have to take L or its inverse and so on, but let's just forget about it. Let's just pretend there is only one eigenvalue, and so you have to decide the eigenvalue of the longitude and the eigenvalue of the meridian. And in this case, it's a computation. Maybe not that easy, but which you can do. Once you've understood it, it's easy. And it's rather simple in these parameters. Okay, so I show the formula to show that it is simple, but it's not very important for me to see what are the polynomials. But you can express the eigenvalues directly in terms of cross ratios. And there is a theorem which tells you once again that whole peripheral holonomy sees a lot of things, is that if you want to compute the differential of the volume, so it's a differential of the sum of dialog. Dialog is a real analytic function, so you can just compute. But you can be clever and you can show that the differential of the volume is only expressed in terms of the peripheral holonomy image. Okay? Well, if you want some formula, I will write it in this way. Maybe it will not make a lot of sense to you, but let's write it. It is a formula that, in fact, that has deep reasons for this formula to be, and it is not easy to prove, and this is not just the result of a computation. This formula has a very deep reason to show it. But, well, just forget about it. It's expressed in terms of log of the modulus of the eigenvalues and d log, the differential of the log. Okay, and it is an antisymmetric formula. So this theorem is due to Neumann-Zagier. In the case n equals 2, n equals 2, and guess what? I was in the with Nicolas Bergeron and Elisha Falbel. I generalize it first for n equals 3 and then for general n.
Maybe you should add Craig Hodgson as well. Craig Hodgson?
Ah, yes. Okay, so it's 10. Yes, right. Okay, so once again, this map, peripheral holonomy, sees something that it seems that happens really, something really three-dimensional, volume of representation, is seen only by this kind of two-dimensional object, that is the eigenvalues of the longitude and the meridian. Okay.
And this formula is for n equals 2, right?
This formula is for n equals 2. I will not write the generalization, but there is a generalization. There is a generalization of the volume, and here you have some kind of antisymmetric expression in terms of the eigenvalues
Okay.
of the longitude and the meridian. Okay. Here it is written for n equal to and only one cusp.
Right.
If you have different cusps, you have to add every contribution. Okay?
Is that a subharmonic function?
No, I said analytic, real analytic
Yes,
function.
real
analytic.
You may consider subharmonics.
Ah,
You differentiate twice.
yes, and in this case, it's okay. In fact, if you differentiate twice, you will have deep links, and I won't go into that with a block group. We will have a map which would be d log, wedge d log, and well, it fits inside a big K-theoretic picture, and I would not be the most knowledgeable to speak about it. It's there is a very broad K-theoretical picture, and that is relying a lot on works of Goncharov. And the appearance of this d-log, wedge d-log, is meaningful. Okay, I cannot be more precise. I'm sorry. It's well, maybe if I had chosen to speak only about that in 3 hours, I may have given insight. But I will just stick to the first derivative. Okay? So, let me briefly speak about the second approach. Recall that defining the volume was a problem. I said at the beginning that there is a volume, there is such a function called volume on the character variety. And here we have an insight. If it's a part of the character variety that you can see by the combinatoric, then it's pretty clear what you want to do to compute volume. You just add the volume of tetrahedra, and you can do that also in higher dimension, just by summing dialogues of cross ratios. Okay, but now we know that there are components that you won't see in this way. For example, the abelian component. Only for the 8-node component, 8-node complement, we just saw one component of the character variety, but the abelian one we did not see. So, the second approach, and I will be very sloppy on it, is via bounded cohomology. And so it's not very surprising that cohomology happened, because volume is like a cochain in cohomology. But the fact that the manifold we are looking at are not compact obliges us to be careful. We cannot just pull back the big picture is that SL2 or SLN has in its third group of cohomology are more or less only one class, which you want to call volume. And when you have a representation of the group, you can pull back this class on M and then evaluate it against the fundamental class of M, and it should give you a number. And this is a theoretical definition in case where M is compact. But since M is not compact, you have to be a little bit worried. And you have, well, there are several ways, but you can use bounded cohomology. So what can I say about that? I can say that there exists a bounded and continuous three cochain, cocycle. beta, which is non-Borel cocycle. In I guess in D3 of SLN C to R, and it is up to scaling. It is unique, this cocycle. And what is that? But it's not so hard to understand, at least in the case n equals 2. So beta, what should beta do? It should take a 4 tuple of guys in SLN and gives number. Okay, and this should be invariant under the global action of SLN, and moreover, it should be a cocycle. That is, it should vanish on boundaries of 5 guys. So I won't write it, but at least I can write the cocycle. I won't verify it is a cocycle. What you can do is, if you have 4 guys, you can look at 4 points inside CP1. Choose someone you call infinity and look at its image. It gives you 4 points, and if you have 4 points in CP1, well, you have a tetrahedron. Okay? And you can take the volume. And as, well, we almost see that this is a cocycle, because the boundary of 5 tuple will represent the 2-3 move with tetrahedra, and so the volume of the thing decomposed with 2 tetrahedra will be the same as the volume of the thing decomposed with 3 tetrahedra. So the sum, alternated sum, will vanish. I won't write this, but with this definition, it's very easy to prove that this is indeed a cocycle. So this is for SL2, and we have understood that SL2 is easier and, well, at least more understood. So this is for SL2, and you have to work quite a lot to generalize that to the SLN case. Okay, but still it exists. It's the work, I will just cite them, of Burger, Bücher, and Niozzi. And now that you have this cocycle, if rho is a representation, you can pull back this cocycle inside the relative 3 cohomology of M with respect to the boundary. And then, well, the volume is the evaluation of this cocycle. Well, I should have written Z, but okay. On the fundamental class. More or less, you do what you want to do, but as M is not compact, you have to work a lot more to define a volume. But a very important consequence of this work is that you have what is called volume rigidity. So now volume is defined for any representation. Well, for abelian representation, it will be 0, but it is defined. Maybe one important thing to say is that the two definitions are compliant. We are computing the same thing, so we can write the same notation for both the function. It's not so trivial, but it is. We define 2 times the same function, and the important theorem is that, which is from Bücher, Berger, Dutzy, is a volume rigidity theorem. So volume has a unique it is true for every n. Volume has a unique maximum on the character variety okay, there is only one representation, class of representation that has the maximal volume. And guess who is this guy? The only one that I showed you. It is obtained for the geometrical representation. Okay. In the case n equals 2, you retrieve the unicity of the complete hyperbolic structure. Okay. This is a way, and for every n the proof is rather recent, but for n equals 2, it's I don't know, maybe 10 years ago. That this proof of rigidity, most of rigidity in this case, has been done through bounded cohomology. Okay, so, well, the 2 most important theorems about the volume are here. Globally, you know that there is a unique maximum, and locally, almost everywhere, at least when the combinatorics works, you have derivative formula. Okay, it's quite striking because with this approach you just have a continuous function. It cannot give you any smoothness on the volume function, this bounded cohomology approach. But still, as it is the same than this volume, well, this is a real analytic function and you can compute the derivative. And moreover, the derivative is just written in terms of peripheral autonomy. Maybe I will keep this theorem. And then I will ask a question. Oh, I should have kept this one too, but too late. Question. Can I perturbate this theorem? I will state it in this way. Is it true that if some guy in the character variety has almost the maximal volume, is it true? Yeah? Then it is almost the geometric representation. I think this is a very natural question. You have a volume rigidity, but can it happen that someone has a very, very big volume with respect to the maximum, being very, very far away from the geometric representation? And this question, well, even in the case n equals 2 is not so clear. I will.
What do you mean by almost?
What I mean by almost, well, you can put quantifier. Is this true that, is there some epsilon such that if you have volume greater than the maximal minus epsilon, then you are in a prescribed open neighborhood of this guy? Okay?
I guess that you think of a divergent sequence with the volume approaching.
Yeah, or
maximum.
in other ways, if you have a sequence of a class of representation with volume going to the maximal volume, do the sequence converge in the character variety to the geometric representation? And so
Are
yes.
there some local maximum?
Uh,
So there is unique global maximum.
that I don't know.
Are there,
Well,
are there zeros of derivative?
Yes. Yeah. I mean,
Yes.
At all parabolic representations.
Yeah, but yes, there are zeros, but it does not mean.
Representations that are
But it does not mean that there are local maximum.
They could be.
Yes, well,
Yeah.
For the right not there, actually, yeah.
Okay. So you can.
But you know, in the neighborhood of the district, it was convex bound.
Yes.
convex.
So what I can say is that it is.
Yeah.
So what I can say is that it is on the neighborhood of this one. This is in, if you choose well-behaved coordinates, it's convex. So here is a nice maximum.
Ah,
Okay, on the whole batch, and you can describe the set on which it is convex. And but then when you are, and it is a set where all the tetrahedra are positively oriented. Okay, and when you go out of this set, it's much harder to track down. And maybe I should ask another question. Is this volume function far from being Morse function? And I think not. And if not, what are the meanings of singular, not singular, but okay, of
The critical point?
yes,
Yeah.
okay, thank you. And I made some experimentation for the 8-knot complement. So there are 4 points. The maximum, which is the geometric representation, the minimum, which is its complete conjugate, and then 2 points at infinity. And points at infinity have geometric meaning. So I think this is quite an interesting question. Is there a geometric meaning to being a critical point of volume? So there are some problems. You have to be careful because volume is not everywhere differentiable. So there are some jokes. But still, you can, well, at least on examples, you can look, you can make nice drawing, and I think that, well, globally, can we get some meaningful geometric information from the consideration of the volume function? Okay, and I will end by saying. By saying 3 things. First of all, well, the first question I tried. I tried a lot with Michel Bucher to deform the proof in bounded cohomology, but at least for now, only for the case n equals 2, but at least for now, we did not succeed. And so I was maybe not desperate, but I would like, I feel like I needed some more information, so I did computer experimentation, and I crafted a test using Snappy to test this conjecture, and I made this test for every manifold with at most 6 tetrahedra in the census of Snappy, that is 1,200 and something. And well, for 40 cases, my test did not answer, so I don't know, but for all the other cases, it is true. So this is the first information. I know that this is true for any n for the figure complement. So at least this example, it is easy to do. But in general, I don't know. But one thing that I noticed, which I think is nice and interesting, is that if this conjecture, well, I said a question, okay, I'm not as positively so. then the generalized Dunfield-Claff-Tillman theorem holds. So this is exactly what I mean by saying, can we get some meaningful geometric information from this map? And this would be an example. If I am able to prove the first part, well, the question, that the question has a positive answer, then the fact that the peripheral autonomy restricted to the geometric component is a birational isomorphism with its image, okay, this theorem of Dunfield-Claff-Tillman, then it holds for any n. And, well, I should have written conjecture because I think it's true, but okay. And, okay, it's, well, in the forthcoming short paper, I explain that. And it's not so clear, I'm a bit puzzled, but I think that in the case n equals 2, the two problems are indeed equivalent. That for n equals 2, for SL2, this property is equivalent to the birational isomorphism of Dunfield and Claff-Tillman. Well, there are things to do, but it may be equivalent. I'm pretty sure for one cusp, and then for more cusps, it's not so clear. So I hope to just check it out, and there will be a forthcoming paper explaining that. And it's not very hard. You have to know the definitions, the bounded cohomology, and so on. But once with the theorems that I wrote, local rigidity, volume rigidity, and volume derivative, it's not that hard to prove this fact. Okay, so I will end here my talk. And if anyone has any hint for this question, let me know. I would be very happy to have the answer. And I think for hyperbolic geometry, it's an interesting question. Even if it is a consequence of the Dunfield theorem for the case n equals 2, it would be very interesting to have a proof from hyperbolic geometry. Okay, not from rational isomorphism of character variety. Okay, not using not using Dunfield theorem.
Could you explain a little bit what's the local volume for SLNC?
Could I explain it?
So,
Okay, I can explain it maybe for SL3,
yeah.
and then it becomes more well explained. Give some hints, okay? Then after that, it becomes more combinatorially involved, but the ideas are the same. When you want to go, so for both definition of volume, the crucial fact is to have a volume of a tetrahedron. So for n equal 2, you have to give a volume to a tetrahedron of an ideal hyperbolic tetrahedron. And in both cases, we just use the hyperbolic volume. So also for n equals 3 or so on, you have to give some volume to some kind of tetrahedron, and it will answer both questions, the combinatorial approach and the bounded cohomology approach. So what are the tetrahedra you should look at? So in the hyperbolic case, you had a combinatorial tetrahedron, and you decorated it, putting some ideal points for each vertex. And here, for n equals 3, you put one flag for each vertex. What if someone here knows about Fogg-Goncharoff works? It is, I'm doing almost a presentation, a quick presentation of the work. So this is a flag in CP2, meaning inside CP2 a point inside a line. Okay? So you have four. The problem now is you have four flags, let's say in generic positions, and you want to compute a volume. Okay? So you don't know what to do because there is no volume, no meaningful volume on CP2. But what you can do is that you can compute four cross ratios. When you look at your collection of flags, let me make an example. So I have these four flags, and I want to construct at least one cross ratio. So I will fix this point and look at these four lines. Those are four lines through a point in CP2. So those are four lines into a CP1. So those are 4 points into a CP1 doing duality. So they define a cross ratio. And you do this trick for every 4 points. Okay. So you have 4 cross ratios. You take the sum of the dialogues.
Oh, that's some.
Sum of the dialogues. Okay. Well, I gave you a definition, but now you have to ensure that this is a cocycle, and this is hard because you have to understand very well the combinatorics of these cross ratios and so on. And mostly, so in fact, we did it by hand in the case n equals 3, and then there is the proposed generalization. There are 2 slide variants, one by, I should say, Garoufalidis, Gunner, Thurston, Dylan Thurston, and Dickert. So this is one team, and there is another team by Dimofte, Gabella. Those 2 guys are more theoretical physics, mathematical physics guys, and Goncharoff. And I personally think that Goncharoff has the good point of view on these problems. So they explain the right generalization of this in SLN, but the idea is the same. You have you have 4 flags in SLN, and you are trying to compute a lot of cross ratios. And you can compute indeed a lot, some n squared, more or less n squared, and you can take the sum of the dialogue, and this gives you a cocycle. And it is not at all trivial to prove that this gives you a continuous cocycle, well defined, even if the flags are not in generic position. And this is the work, really this is the work of Bücher, Berger, and Yotzi in their paper. The new, for generalizing for the volume rigidity, well, the idea of the proof is exactly the same that for n equals 2, but really the new input is that they prove that this procedure gives you a continuous cocycle, which is needed to make all the stuff work. And well, you have to work to do that. You have to. If you are not interested in that, you can just take the definitions. But if you are really looking for bounded cohomology, you have to understand the definition.
Any further questions?
As this big.